Hello everyone. Let's try this method then after the failure in the streaming. Today I want to talk about elastic energy and waves, but not everything about waves, but I want to focus into echolocation and ultrasound, which are two topics that are at the end of the topic of waves and I think is fascinating. Elastic energy is for everyone, doesn't matter the set. Echolocation and ultrasound, I think, is only for set 1 or DCC physics only. Keep that in mind, those who are not doing it, so you are not getting stressed about something you don't need to know. Right? I don't want to take this much longer. Let's go to the lesson. So, about elastic energy, the most important part is what is called Hooke's law. And Hooke's law is something very simple. Hooke's law says that the elastic force is directly proportional to the extension. Important, we are talking about elastic objects. Not all the objects, they are elastic. Elastic objects are the one that when you apply a force on them, you deform them. That's the word we need to use, deform them. But once the force is not applied any longer, they go back to their original shape. They return to the original shape. That is an elastic object. Something that is not elastic is what we call, in this case, plastic. Something plastic is an object that you apply a force, you deform it, it does not return to its original shape. Also, something important that they like to ask is what is elastic limit, which is this idea of something is elastic up to certain limit, that if you continue applying a force and increasing the extension, there will be a point where you're going to break them and it will just not continue being elastic. It will not be able to return back to the original shape. There's one formula in there that say force is equal to K times delta X. That delta X means extension. And that K, is a spring constant. Not all the elastic objects, they are equally elastic. Some objects are more elastic than others. And because of that, we have a spring constant, which is measured in Newton per meter. That is the unit for a spring constant. If the spring constant is very high, it means that with very little force, the extension increases a lot. If the spring constant is very little, it means that you need lots of force to get lots of extension. Just that. Now, also something relevant, when you, let's come to here, when you do a graph, force, here is fine, force divided by extension, you see that it is a straight line and it should start from 0, 0. Important, extension is how much is the length changing. Okay, it's not the final length. It's not the initial length. It's the difference between the final length and the initial length. So extension always at the beginning is 0. So when you're drawing a graph for Hooke's law, force in the y-axis, extension in the x-axis, straight line passing through 0, 0. From the gradient of this graph, you get the spring constant. Sorry, I need my tea. Let me show you one exam question that was difficult, 2025. It was a 6 mark and we could solve it using elastic force. There are two methods to solve it, okay? But let me show you. So it is this one. You will see the activity now. All right. Let me remove my logo. There you go. So pulling the handle compresses the spring in the device by 0.075 meter. That is extension, okay? When the handle is released, the energy stored in the compressed spring is transferred to the toy car. There is a toy car. The spring constant is 64 Newton per meter, meaning that to stretch it 1 meter, we need to exert a force of 64 Newton. No problem here. And they give you the mass of the car, and they ask you calculate the maximum possible speed of the toy car after the car starts to move. Use the physics equation sheet. We don't have it, we don't need it because we remember the questions by heart. And look, it's a 6-mark question. Okay? So as I always say, the first thing we need to do when we have a question of this type is to write down all the information that we have. Okay? That's the first thing. So they say that the extension, better, right? Let me make your life more comfy. Extension. Aha, now it is good. Is 0.075 meters. Spring constant, K, is equal to 64 Newton divided by meter. And the mass of the car toy is 0.052 kilograms. Seems okay. Remember that the letter for extension or change of extension is delta, which always means change. X is extension. All right. With this information, what can we get? We could find out the force, but I think that what they're asking us is the velocity. Is there a way to connect force and velocity? Yes, there is. There are different approaches to this, okay? There are different approaches. Let's call it method 1, method 2. Let me remove the question, which is going to give us more space, and put my logo. Yes. All right. So we could use the method that I call it using elastic energy. Elastic energy, EE, is equal to, this is an E, okay? I have had many complaints about it. 1.5 K times extension square. That is a method, all right? Why this is a method? Because we have an elastic, we have a spring, we use it, we deform it, we release it, choo, and that is going to transfer that energy, in this case, to a toy car. And that is going to make the toy car to move. So clearly there is a transfer of energy. What transfer of energy is happening here? It's going from elastic energy to kinetic energy. And how this approach is easy, because we could go from elastic energy into kinetic energy. And if you remember, the formula for kinetic energy is 1/2 mass times velocity squared. So we could find out in this way very easily, thanks to that transfer of energy, how much is the final velocity. This is approach 1 or method 1. And this method is completely fine. But since we are using elastic force, there is another way to do it. Force, we said, that is K times extension. No problem. Also, force, according to Newton's second law of motion, is mass times acceleration. And there is a Suvat equation that says that v squared minus u squared is equal to 2as. You see, there are different approaches to get that final velocity. All right? Am I missing any part of? No, that's all. So let's solve it through both of them, and you will see that the result should be exactly the same. I call this method 1, and this we're going to call it method 2. All right? In both cases, we should have the same result. Let me get my calculator. Okay. Now you go. So, for elastic energy will be equal to 1/2 times 64 times 0.075 square. elastic energy is equal to, just give me a second, calculator, 0.18 joules. If you are into standard form, it could be 18 times 10 to the power of minus 2 joules, okay? But there is nothing wrong with 0.18. And now that we have the elastic energy, there will be a transfer of energy from elastic energy into kinetic energy. We assume that there is no energy wasted or energy dissipated. It's just 100% of the elastic energy goes from elastic to kinetic. So the kinetic energy is going to be also 0.18 joules. 0.18 joules is going to be equal to 1.5 times the mass of the toy times velocity square. And here we have one of the changes that causes most problems for students. Let me recap, okay? If kinetic energy is 1.5 mass velocity square, velocity is equal to 2 times the kinetic energy divided by the mass and all the square root. So many times students don't get this rearranging correct. And I'm sorry, but I have to blame math teachers for this. How can you not know this simple rearrangement? Anyway, we're not blaming anyone now. We're just solving how much is this. V is equal to 2 times 0.18 divided by the mass. And the result of all that is going to give us the velocity, which in this case, let's go to calculator again, is approximately 2.6 meters per second. I think it's a very easy 6-mark question, just with 2 calculations, one to calculate elastic energy, a bit above, and another one to calculate velocity, 6 marks for this. I think it's quite cool. But as I mentioned, there is another way to do it, which is also quite cool. So, and also it's about what we were talking earlier, which is elastic force. So let's move the camera a little bit. Fantastic. So force is equal to 64 Newton per meter times the extension, which is 0.075 meters. You see, Newton per meter times meters. Ciao, ciao. So it's going to give us the force in Newton as it should be. And this is going to be equals to 4.8 newtons. And as I mentioned, and we know very well because we are studying already, second Newton of motion said that force is equal to mass times acceleration. Therefore, rearranging it, acceleration is equal to force divided by the mass. So we can calculate the acceleration of the toy. Alright? Which in this case is going to be equal to, acceleration is equal to 4.8 divided by 0.052. And this is equal to 46 times 2, careful with the units, meters per second square. This is the acceleration. I know you might be thinking that this method is longer than the other one because it involves 3 calculations. First, we need to calculate the force, then we need to calculate the acceleration, and then once we have the acceleration, we use a Suvat equation to calculate velocity. But it's an alternative method. It's an alternative method, and if you are not good rearranging equations and you don't know how to rearrange kinetic energy, it is also a method. So now that we have that V squared minus U squared is equal to 2AS, where this S normally would be distance traveled, but in this particular context, it would be the extension, okay? So V squared, which is what I'm trying to find out, I don't know, minus U. U means initial velocity. We have no information that the toy was moving before. Actually, we assume that if you are using a spring to move it, means that the toy was not moving before. So it is 0 squared is equal to 2 times, how much was the acceleration? Sorry, 46.2 meters per second square times the extension 0.075 meters. Velocity square is equal to 6 times 923. We can round it to 693, and then v is equal to the square root of that, which is 2.6 meters per second. As you see, doesn't matter what method we follow, we are going to have the same result. In both cases, we need to use elastic energy. Well, in one case, elastic energy, and in the other one, elastic force. So just to summarize the methods, in method 1, method 2, in method 1 we go to elastic energy into kinetic energy, and from kinetic energy we find the velocity. What is the advantage of this method? There's only two calculations. Disadvantage, the formulas are both of them longer, but if they give them to you in the equation sheet, that shouldn't be a problem. But the rearranging, maybe you find it more difficult. In the method 2, what we did is force, but elastic force. From elastic force, we find out the acceleration based on second Newton's law of motion, and from acceleration, we calculate velocity using a Suvat equations. This is another example of different ways that they will, both of them go to the endpoint. Depends on the information they give to you, depends on the formula you want to use. You're going to use one method or you're going to use the other. Okay? I think elastic force is pretty simple. And most probably they will combine it with elastic energy. So pay attention, because one is in topic 1 and the other one is in topic 10. All right, fantastic. Now I wanted to talk to you about echolocation. So I will use my, not this, but this. Anyone knows what is this? This is an image of, obviously this is a baby growing, and this is an ultrasound scan. Okay, what is ultrasound? So the human hearing goes from, I think it was 100 hertz to 20,000 hertz in terms of frequency for sound waves. Remember that sound waves, they were longitudinal waves, but they still have frequency and wavelength. And they are very useful because they could provide us with lots of information thanks to this large frequency. One of the uses that ultrasound they have is this kind of images, an echo image. It's like same as echo actually. That's why this is called echolocation or echo scan. Why do we use ultrasound to see the fetus? Because the other alternative would be to use X-rays. But X-ray is a type of electromagnetic wave that could affect the development of the fetus, so it's not good. Actually, you know that women who are pregnant, they are not recommended to be around X-ray area in a hospital. But with ultrasound, we can get those sort of images. In a second, we're going to see another use. Another use is, for example, a sonar or a radar. Another example, same principle, would be bats, dolphins, whales, any other animal that use echolocation. Normally animals that they use echolocation is because they don't have very good sight, they cannot see very well, but this system gives them lots of information. How does this work? So ultrasound waves are sent and they will collide with objects. And when they collide with objects, they will bounce back, and then the animal, or in this case the ship or the submarine or the machine like we saw earlier, will receive the wave bouncing back, and depends of when those waves they reach, we're going to know the distance. and then a computer is collecting all that information and making an image. We could do something much more simple than this because our systems, our feelings are not designed to use ultrasound. But when you enter in a room and you emit strong sound, by the way that the sound comes back to you, you can sort of understand how big the room is. If you emit a sound and you receive echo, it's because probably the room is very big. That's why there is echo. If very quickly you don't receive any echo, you understand that the room is not very big. You can try, close your eyes, emit the sound, and you will also feel that the waves are bouncing back to you. What sort of questions they can ask you? Based on the example of the ship, they can give you something like, let's go. So, don't judge my drawing, okay? Normally I draw much better than this. Okay. So imagine that they ask you the distance between the ship to the bottom of the water, okay? Or to here. Because they want to know if they can use this ship in here, because you know when it is very shallow, the ship could collide with the floor, okay? It would be more like here. There will be some part of the ship in thanks to upthrust force. And they ask you, how much is this distance? You don't know. How do you do it? You emit waves. By the way, dogs can also hear ultrasound. And then these waves, when they collide with the bottom, they will bounce back. And it will reach back to the ship, sorry. And they tell you that the time that it takes from you to emit the waves up to receiving them back is 0.15 seconds. The time, it shouldn't be very long. It shouldn't be very long. If the time is very long, something is not going well in there. And now you're thinking, and what can I do in here? Don't worry, because they need to give you a way to calculate the velocity of the waves, okay? They can give you, for example, the velocity. They can say the velocity of sound in water, which is, they can say that, look, velocity of sound in water is 1,500 meters per second. They can give it to you directly. Or, if you don't want to make the question more complicated, they can say, well, we give you the frequency, which is 20,000 hertz. And we give you the wavelength. Sorry, but I don't know this information by heart. Wavelength, ultrasound. That's an example, okay? They can say that 0.77 millimeters. I'm just making this up, okay? Because he said that that's the wavelength in tissues, but never mind. Let's say that they can give you or the velocity directly. They say the velocity of sound waves in water is this one, or they give you information that you can use to calculate the velocity. Remember that wave speed, and this works for both transverse wave or longitudinal waves. The formula is the same. Wave speed measured in meters per second is equal to frequency times lambda. Please don't forget that this sign is lambda which means wavelength. Frequency is measured in hertz. If you see kilohertz, you need to multiply by 1,000. And here it is in meters. And remember that I give you, for example, millimeters. You need to divide by 1,000 to get into meters, okay? But in this case, just for this activity, we will go to the easy option. No, it is easy option. They give you directly that the velocity of ultrasound in water is 1,500 meters. What do we do next? If you remember, velocity is distance divided by time. Velocity in meters per second, distance in meter, time in seconds. No problem. But we don't want the velocity, we want the distance. Distance is equal to velocity times time. I really hate to do this, but this is the triangle, okay? Velocity, distance, time. I don't think any year 11 that wants to do science can still use these triangles. You should be able to rearrange formulas, but you never know who is on the other side. Anyway, what time and what velocity we need to use? You will automatically think, well, this is very easy then. Distance is equal to 1,500 meters per second, 0.15 seconds, and that gives me a distance of, I think I'm getting sick. This is the problem of working with children all the time. 0.15. This is 225 meters. If you write this answer, they're gonna give you 2 or 3 marks less. Why? Because this distance, 225, is the distance from the ship to the ground and back. So the actual distance between the ship to the bottom, the sea bottom, is the half of that distance, okay? That distance you just calculated is this one, to the floor and back. So the actual distance to floor is 225 divided by 2, which is 112.5 meters. This is the distance that you are looking for, okay? This is the actual distance that you are looking for. And the same principle works with any other type of ultrasound that we are talking about. We have talked about the sonar, we have talked about the scan for the babies, we have talked about echolocation, animals, and I give you a few examples. Sorry, you can see the internet is very slow. Apologies. Exactly the same principle. All right? Exactly the same method. I have never seen any question in physics GCSE where they ask you with animals. I have seen with sonar. I have seen with the ultrasound for baby scan. And actually in biology, they ask you why we use ultrasound instead of X-rays, and I mentioned earlier the reason. Go back and check at the beginning of the video why. But just in case of, is exactly the same principle. All right? Now, before we go, I want to talk briefly about seismic waves and why seismic waves are relevant for us. By the way, seismic waves means earthquake, okay? Those who study geography, you know that, well, and in science we have studied that too. You know that the Earth has different layers. Different layers. We have crust, we have the mantle, and we have the core. But always people could ask, like, and how do you know that? How do we know that? Because the deeper we have ever gotten is never even to the inner mantle or the inner core. We don't know. We have never seen experimentally, well, no, we have never seen empirically how the layers of the Earth they look like. However, seismic waves and earthquakes, they give us lots of information about how the Earth is really inside. Okay, I'm talking about, this is the crust, this is the mantle, and this is the core and inner core. And normally the diagrams, they show a pizza diagram like this. This being the crust, outer mantle, outer core, inner core. Okay? And how do we know this? And we can even study, or we can even predict what materials we are expected to find in each parts of the layers of the Earth. It is thanks to the earthquake, because the earthquakes, they are waves, and there are two types of earthquake waves. One is called P waves, and the other one is called S waves. And why one is called S and the other one is P? To distinguish them, basically. P waves, I don't remember, one was also slower than the other one. I think P waves, they are faster. So P waves are faster. S waves, they are slower. And also, super important, P waves, they are longitudinal. And S waves, they are transverse. And here comes the magic part. If you remember, when we studied longitudinal waves and transverse waves, depends on the material they are traveling through, some waves will be traveling faster. So transverse waves, they go very fast. They go very, very fast when the material has low density. For example, the speed of light in vacuum is 3 times 10 to the power of 8 meters per second, which is the fastest in the universe. You cannot go faster than that. But that is transverse wave. And that's happening in vacuum, meaning nothing at all. But light, if you put light into water, it travels slower. And if you put it into something even more dense than water, even slower. That's the idea. Transverse waves, they travel very fast when the material has low density. However, longitudinal are the opposite. They travel the faster when the material has high density. So P waves, they will travel faster when they are going through materials that they are like solid. Like, for example, the inner core is solid because of the huge amount of pressure. Okay? And some materials in the mantle, they are also solid because of the pressure as well. So P waves, they will travel very fast in the layers of the Earth that they are very dense, and they will travel slower when they are traveling through. It's not exactly a liquid, it's like magma, but let's say like it is a liquid state. So based on the speed of the different velocities and how they reach to different parts of the planet, that gives us an image of the different layers of the planet in the same way that when we use ultrasound, it gave us an image of how is the baby, or if you have a sonar, how is the area around, or if you use a submarine, how does it look like. So when you have all that information together, you have something like this. You will see how cool this is. If I manage to, here it is. There it is. So look, let me zoom a little bit. So these waves that they cannot pass through, you see the crust, mantle, and it's getting more solid. These waves in here, they're doing like a curve, they are what we call S waves. And we know that they are S waves because they cannot pass through the solid areas of the layers. And you see that depends on that, they get some sort of reflected, and then based on the point where they reach on the other part of the planet, because whenever there is an earthquake, the earthquake is felt in different parts, and we have tools and machines to measure the earthquakes in different parts of the planet. So based on that, we can have an image on where is the earthquake and how big it is and what is the magnitude. And then all these waves that they pass through the inner core, which is solid, they are P waves that they travel faster in there. And you see that what is happening is refraction. Remember that refraction is when waves they pass through two materials with different density. And based on that, once they reach to the other part of the planet, all this information give us the image that we have about the different layers of the planet. I think it is absolutely fascinating, and I encourage you to research more about it. What you need to know, two types of waves. P waves, they are faster, they are longitudinal, and whenever they pass through a material that is more dense, they travel even faster. S waves, they are slower, they are transverse, and they cannot pass through solid. These together give us a picture of how inside the Earth, how does it look like, and is what we use in geography to study, or better said, geography and geology to study our planet. Okay? I think that is more than enough for today. I think we have managed to have a very nice video of 40 minutes. Lots of information, elastic force, we solve exam questions, 6 mark. We also talk about echolocation and ultrasound, and we ended up with seismic waves. Quite complete session. I will try to go back to streaming once the internet works well. See you soon, guys. Stay tuned.